Thanks to Nick and Chris for inviting me in this fabulous event so far, and I really look forward to the feedback on this talk and having a discussion with you. And I want to encourage you to interrupt in the middle. I'm very open to questions as we go along, so don't hold back until the end. I wanted, by the way, for the title to be something that seems unusual in the sense that physicists don't often focus on theories of origins. So part of the hope with the title was to indicate that in some ways thinking about a theory of origins is an unusual kind of project for physics. And I think we can see that this brings out a number of questions about how to approach this kind of theorizing. What are we doing in theorizing about the origins of the universe or about the origins of the system? And it's a context where I think there's really actually conflicting intuitions about how to approach this methodologically. And I want to introduce a few different ways that people have approached questions about how to theorize about the origins of a system by looking first at a historical case where I think we might have a clearer sense of how to think about these different ideas. So in the 17th century, or 16th and 17th century, the great cosmological question of the day was, what is the structure of the solar system? And how do we think about the causes and forces that determine the motions of the solar system? And in that context, then, the philosophers and physicists of the day were asking how to think about the origins of the solar system, given these new ideas. So one possibility was to say, if we're going to explain the origins of the system, we should go for a view which I'll call indifference. So even starting in chaos, as confused as any of the poets could invent, by the laws of nature alone, everything would in the course of time have come to be just as we now see it. The world as we now see it is entirely indifferent to the initial state. So this is the possibility that the laws would completely determine the structure of the solar system without any commitment about what the initial state would be like. Now there's another possibility, which is that there'd be some kind of selection involved in choosing the solar system as it was. So on this view, mere mechanical causes cannot account for the elegant system of the planets, with extremely regular motion of the planets and their satellites, all in the same direction and nearly in a single plane. This improbable arrangement can be best explained as the result of a specially chosen initial state. And there's different views about what could be involved in such a choice of initial state. And finally, there's a different option, which is to say that perhaps our solar system is just one among a huge ensemble of solar systems. So our planetary system is but one of an infinite number scattered through the infinity of space. Among this infinite ensemble, there will be many that, like ours, have physical features suitable for life. And so we explain the apparent features of the solar system by virtue of anthropic considerations. And so the first two are really paraphrases of Descartes and Newton. Newton gives a design argument in the General Scholium. That's the end of the Principia. He's concerned about the stability of the solar system and how it is that the planets all revolve in the same direction within the plane. Descartes, before him, had suggested that the laws that he had proposed were sufficient to account for the solar system regardless of the initial state. And the final, it's not really a paraphrase, but this is a summary of Giordano Bruno's position. Now, obviously, in some cases, these positions were quite firmly held. Whatever your complaints about peer review, Giordano Bruno had a different, very negative experience. So this was a firmly held commitment of his that he stuck to despite 8 years of trial and the horrible result.
These days we call it cancellation.
Exactly. So, but I think this is an interesting context. So historically, we can look and see how did these methodological principles contribute to understanding the solar system. So obviously these were views that guided in some sense the research of these different figures. And so I'm calling these methodological principles. Maybe you could think of them as preferences as well. It's not clear that principle is the right word here. But to what extent did these ideas guide or impact inquiry into the dynamics of the solar system and its formation? And more to the point, to what extent should they have done so? Do we think it would have been proper for these principles to play a role in guiding research? Yeah?
So does these exhaust all the possible different approach to a theory of origin?
I don't... Oh, Jesus.
It's just...
I don't mean this to be exhaustive. I don't know that there's another that comes to mind immediately that was prominent during the period. So I didn't mean to be exhaustive, so there might be others that I'm missing, but none other come to mind unless you have one in mind.
No, I can't really see anything else, that's why I'm asking you.
Yeah. No, so that, I mean, I think I've covered the main ones, although there might have been other ideas that were pursued. But one thing I think that by looking at this historical case, I want to raise a concern about whether these principles should have guided research. So let's take Newton's position here as an example. So he was particularly concerned about, so in the context of Newton's argument, he was arguing against the vortex theory of planetary motion, which had a very natural explanation for why all the planets move in the same direction. So he was puzzled about that, and he was also puzzled about the stability of the solar system because he thought comets were quite massive. So if you think about it, it was quite a while before you could estimate the mass of comets, and if you have comets slinging through the solar system, sometimes retrograde, it's natural to worry about whether you have a stable system. And so he thought that this must be evidence of design, providential design, that this system actually works. But I think this reflects a general worry here that I call this an illusion of contingency, right? So Newton was responding to what appear to be just contingent brute facts about the solar system. But it turns out that these targets of explanation really just reflect the incomplete understanding of physics at the time. So after doing more physics and trying to understand how solar systems form, I'm not faulting Newton. Obviously, this was a lot of further work that had to be done. You then have an account of why the planets orbit in the same direction because of the way they're formed, and also the stability of the solar system. Obviously, again, that's a huge enduring problem in celestial dynamics, but we first have a different estimate of the mass of the comets, and we now have a better understanding of why the solar system, well, it's actually not completely stable, but why it's as stable as it is. So in this case, I think Newton's response is unnecessary. It's something that he shouldn't have been invoking selection to explain, but of course in his position it was hard to see that future physics would resolve these problems in sort of more traditional ways. But I mean this to raise a worry that if we're appealing to these principles, if we move to appeals to selection or these other effects, we might be doing so prematurely, just in the way that Newton did. So I do think that these views have played a role in approaches to the early universe as well. So I'm going to claim that at least in some of the discussions in cosmology, I think these views also are in the background. And I'm going to be pursuing the question of whether they should guide inquiry in early universe cosmology. And in particular, so again, this is much more of a philosophy talk, but the one starting question is just, should we expect these principles to guide us to true theories? So if we want to accept them as methodological principles, why should we think that they will lead us in the right direction? So is there any reason to think that accepting these principles are likely to lead us to develop true theories? You might, for example, accept some substantive a priori metaphysical assumptions about the nature of the world. I'm inclined to try to avoid that as far as possible, but if you're inclined to that, that might give you a reason to prefer one of these. Or you could, if you're more empiricist leaning as I am, you could try to see whether they have been fertile in the past and say there's sort of a record of past success when we followed these sorts of principles and appeal to them in that way. I also think there's a really interesting interplay between these sort of general principles or guiding ideas and questions in foundations of physics. And so this is more what I'm going to be pursuing today. Namely, how should we think of these principles and sort of instantiate them in a specific context? So when we're thinking about early universe cosmology, what is the content of the principles in more detail? And are they justified when we cash those out in this context? How should we think about the demand for indifference in this kind of setting, for example? And I'm going to be mainly critical. I think in a lot of cases, the principles, when you try to cash them out in terms of research programs in cosmology, are not all that compelling. So I'm going to be arguing sort of overall against using these principles as a guide for research. And secondly, I think there's an interesting interplay between these sort of ideas and a question that I'm going to just characterize as where to seek explanations in cosmology. So what I mean by that is partly in early universe cosmology, you can think of the different energy scales as you go back towards the Big Bang, and you can ask, at what energy scale do we expect to solve certain problems, right? So at what energy scale should we expect to explain certain features of the universe? And I think there's an interesting interplay between these principles and the kind of way you'd answer that question, right? So do you expect energy scales at a certain level to resolve the horizon and flatness problems and so on? That's related to a commitment to indifference. And so I think this is there's an interesting interplay as well in detail between the general ideas and how we target certain areas for explanation. Okay, so before saying some things that are more critical about the general principles, I'll do a little bit of background, and this overlaps a bit with what Marie did already. So again, the standard model of cosmology in one slide. So this is, so there's a huge amount of observational evidence in favor of the standard lambda CDM model. You can find a lot of different illustrations of this form. In this case, the universe culminates in the creation of the WMAP satellite, so I think you know who created the image. But the quote I have here is from a recent book by Peebles, where he emphasizes, he's talking about structure formation in particular, that he sees the universe, this history, as an evolution from order to chaos, and in particular, the initial state of the universe is strikingly simple, and then we have increasing complexity as we evolve forward. Let me say a little bit more about this. So again, I'm sure you've all seen these images. So this is 3 of the observatories that looked at the cosmic microwave background. And you can see with COBE, we had the temperature and the fact that it's a black body is an amazingly close fit to a black body spectrum. But of course, the temperature was very uniform. It's uniform to 1 part in 10 to the 5th, and so it was only with WMAP and Planck that we started to see those temperature anisotropies. So I like this image just because you can see the increasing resolution as we go through the history of these observatories. And what we see now, again, summarizing a huge amount of work very, very quickly, is that we do have a very simple initial state, and this is a huge boon to cosmologists, because we can use linearized perturbation theory to describe the evolution of that system. So we have a system that looks like a FLRW model, overall a uniform geometry, with small perturbations, which we can characterize as Gaussian, adiabatic, nearly scale invariant. And you can use these observations to also put very tight constraints on the cosmological parameters for the lambda CDM model. And as is often the case, a scientific field often really flourishes when there's a source of evidence that you can keep going back to give more and more refined observations. That's been true with the cosmic microwave background since it was first discovered in 1965. So we can see here sort of the later stages of the evolution where we have satellite missions that have given us increasingly precise observations of the CMB. And this has really spurred early universe cosmology because you have an incredibly rich source of data that you can turn to as you ask further questions about the early universe. And so in terms of targets for early universe theory, so here's a way of posing the question. What do cosmologists gain by extrapolating backwards from the CMB, rather than just imagining that we start cosmology at that point and take that as an initial data surface, right? So what is it that you would miss if you just took the data specified on the CMB and evolved forward from there? Well, first of all, you'd miss a lot of exciting physics because the physics in the early universe is high energy physics. There's a lot of things that we can only look at in the early universe, so you'd miss out on that. But you also wouldn't have answers to all of these questions, right? So by extrapolating back from the CMB to earlier times, you can give physical answers or try to propose physical answers to these questions. So first, why does the universe have specific light element abundances? So that's answered by the account of Big Bang nucleosynthesis. Why is there a striking asymmetry between matter and antimatter in the universe? This is still an open question. There's proposals for baryogenesis that would account for why we have this asymmetry, but it's still not something that there's a canonical model for. And so in some sense, I think we're going to more and more open questions. Why does the universe have flat, almost FLRW geometry? So why is it that the CMB is so strikingly uniform? This is something that was quite surprising when people first made those observations. And then finally, why does it have those very specific perturbations? So again, this was before the CMB measurements were made. People were aware that you had to have something like these kinds of perturbations to work with later accounts of structure formation. So Peebles and Harrison and Zeldovich had already said before the CMB observations that you need to have a nearly scale invariant spectrum of perturbations that would then grow into galaxies later. But then with the observations, you can characterize these more precisely, and you want to ask, what's a causal account, or what's an account of how those arose in the early universe? And so the CMB gives you an enormous source of precision data to constrain proposals to answer these kinds of questions. And why do I say that this is, why should we think of this as a theory of origins, right? So why should we think of this as involving origins or the initial state? Well, that's mainly because of the classical singularity theorems in general relativity, but then the question naturally arises, what are the limits of classical GR? So I'll go over this relatively quickly because Marie already talked about some of these issues. So there's early singularity theorems going back to the 30s. I'm going to describe this in sort of contemporary notation. So this is Tolman and Ward in 1932. So again, this might be familiar to many of you, but the basic idea of their, that was really the first singularity theorem. If you take, again, a lambda equals 0 model and you have a perfect fluid, and that just means that the energy density plus the pressure, 3 times the pressure, is greater than 0. So they're asserting an energy condition there, although they didn't use that terminology. Then Einstein's equations imply that if you have a bundle of time-like geodesics, that the area, cross-section area of that decreases. So there's a focusing effect just due to the attractive nature of gravity. They have, they're considering an FLRW model, and so you just have an initial assumption that you have an expansion that's greater than 0. So, sorry, H0 is the Hubble constant, so that's a characterization of the rate of expansion. And so you have some slice where the universe is expanding. You have this focusing condition. Then they have, again, they weren't explicitly using this language, but you assume that the causal structure is nice, so you don't have close time-like curves and so on. And then you're able to show, again, this is the simplest case where you have a huge amount of symmetries. You're able to show that all time-like geodesics have a limit on their length. So there's a finite time such that the scale factor goes to 0, and all the physical quantities like the density go to infinity within that finite time. And so all path-directed geodesics have a finite length. So this is an early version of a singularity theorem, and obviously at this point you could ask, how much does this rest on the assumption of symmetry? Because we've used the FLRW models. Sorry, I'll go into a little bit more background here just to explain the components. Again, I don't know, this might all be familiar, so I'm counting on what I've heard called the Fermi pleasure principle, which is never underestimate the pleasure of hearing something that you already know. So the elements that go into these singularity theorems are, first of all, the Reishidui Equation, which just characterizes how the congruence of time-like curves behaves, right? And so if you expand the theta term here, characterize the expansion of the congruence, then you have different terms corresponding to the shear, that's a volume-preserving effect, the twist, and the Ricci tensor appears in the last term here. And if you take a congruence that's initially orthogonal to a hypersurface, then you can neglect the twist. And the second term, the shear, is non-negative. And then if you also, and this is implicitly imposing an energy condition, that last term is going to be non-negative as well. and that's, again, assuming you have matter that has sort of positive energy density or satisfies the other energy conditions, then you'll have basically that characterizing the fact that gravity is a force of attraction. And if you include those assumptions, then we have the equation that just simplifies to this. And what that shows you is that the expansion is constrained such that if you initially have a negative expansion, so again, if we're now looking backwards, we have a congruence that's initially focusing, then that will run to infinity within some finite time. And so what you'll have then is a creation of conjugate points, which is a contradiction with the idea that you have geodesically complete curves. So again, I'm sorry if this is review. And so schematically, so we had the early singularity theorem from Tolman and Ward. More schematically, you have a set of assumptions that you can then see how much you can loosen them. And so you have to have some assumption about focusing or convergence due to positive curvature. That's what I was just describing. Then you also need to have some kind of geometrical initial condition. So in the Tolman and Ward case, we had a complete hypersurface and then expansion, but as Marie described, you can also have a closed trap surface. That's what Penrose introduced in 1965. So we have to have some kind of geometrical condition saying at some point in the spacetime, you initially have a setup such that you have some focusing. And then there's also an assumption about causal structure, and that gives you an assurance that within some region there should be geodesics. There should be complete geodesics. And what we have then is a kind of reductio argument. So the singularity theorems all basically show, given the geometrical initial condition and focusing, you'll end up with focusing so that you have conjugate points, and that contradicts the existence of complete geodesics. So they have the form of a reductio. The first two assumptions conflict with the existence of complete geodesics, and so that means that you must have incomplete geodesics, curves that in some sense run out before they should in the spacetime. And that's now usually accepted as the kind of working definition of what it means for a spacetime to be singular. And so, again, the first theorem that I mentioned, Tolman and Ward, was very specific. It included a lot of symmetry assumptions. And so the natural response was, well, maybe that only holds in those specific models. In the mid-60s, the work by Penrose, Garrosh, Hawking, and various others showed how to generalize these theorems quite considerably and remove the assumption of symmetries. But again, there's a shortcoming of these is in that what they reveal is the existence of incomplete geodesics, and they're not particularly informative about other structures. You might want to know more about the singularity, but the singularity theorems really just give you a reductio argument that that there are incomplete geodesics. So a kind of typical response, there are tons of quotes to this effect, but this is from Kip Thorne, 1967, so shortly after these general singularity theorems were derived. He says, from a purely philosophical standpoint, it is difficult to believe that physical singularities are a fundamental and unavoidable feature of our universe. On the contrary, when faced with a theory which predicts the evolution of a singular state, one is inclined to discard or modify that theory rather than accept the suggestion that the singularity actually occurs in nature. So this is a fairly standard view in physics. And so singularities are taken to indicate the incompleteness of GR. I think there's some qualms about exactly how that argument goes, but let me run with it for the moment. So in the simplest case of the FLRW model, I think you can give a very strong argument as to why the singularity indicates that GR is incomplete. And that's because you actually do have something like the blow up of curvature invariance, the densities and so on blow up as you approach the initial singularity. That's true along all past geodesics. It turns out that this is, the discussion of singularities has revealed that there's a huge and varied different ways that spacetimes can be singular. And so I think in some of the other cases, it's a lot less clear what to say about the results where you claim that they're singularities, because the singularities are not always linked to curvature pathologies in the way that they are in the FLRW case. And there are other cases, which Chris Wutherick and I have worked on at a few points, where there's other ways in which GR might not be complete that don't correspond to singularities in the same way, namely that there might be Cauchy horizons, which mean that there's a limit to the domain of dependence that can be predicted from a surface. That also indicates, in some sense, an incompleteness of GR, but it's a different character. Yeah?
Would you say that if the singularities were at past infinity, would you be more comfortable with them?
Would I be more comfortable with them?
Or community in general?
Well, in some sense, this is why I said it's a little. So I think the standard physics line is that this indicates that GR is incomplete, but in some sense, even in the FLRW models, it's a globally hyperbolic solution, and so in that sense, there's no point at which you say, okay, we can't use GR deterministically to evolve the solution even further back in time. And so this is related to the fact that there's really no local analysis of singularities that seems to capture all the intuitions that Thorne and others have when they say there's something wrong with singularities that indicates an incompleteness of GR. So you'd like to be able to say there's like a singular region where things blow up or something like that, but that doesn't work. The singular region can't be a part of spacetime, so instead you have to say something like there are incomplete geodesics, or geodesics are approaching a point which you have to treat as like a compactification or a boundary that you add onto the manifold. So I'm actually somewhat skeptical of these arguments, but I think in some cases you can make a different argument that yes, we should acknowledge that there's a limit to the domain of applicability of classical GR, which corresponds to as you're approaching the singularity. But I wouldn't want to say in general that we have an understanding that would justify that. Yeah, Mike?
How much should I be reading into underlining all? Because I kind of feel like I'd be already on board to be terrified if just one.
Oh, this is just because it's so symmetric. So I was emphasizing that in the Tolman and Ward case, you actually have a claim that's about all geodesics ending. And that does seem like a much stronger claim than just there is one that ends, right? So, yeah, I emphasize that partly just to...
Not for the poor guy that falls in.
yeah. Okay, so as I said, I already said this to some extent in response to the question. So I think there are cases where there are additional grounds for thinking that GR is incomplete, above and beyond just the existence of the singularity. So when you have cases with curvature blow-up, I think you can make a case that you would expect, as you approach regions with curvature blow-up, that you would have strong gravitational fields and that you might have quantum effects relevant in that regime. And so, as I said, there are, I think, not compelling cases to say that we should treat all singular spacetimes as incomplete in the same sense. I think there's a pretty wide variety of singular behaviors that have been classified now. I don't think there's a one-size-fits-all kind of prescription for that. This is something that Eric Curiel has emphasized both in a paper a while ago and in a more recent Stanford Encyclopedia article. Okay, so this was meant to just be a bit of background to say, why am I talking about theory of origins? Well, it's partly because we do have to say something about, in the early universe, how we either modify GR. Again, so I think in the case of the early universe singularity, we do have reasons to think that there's a limit to the domain of applicability of GR as we go back towards time, as time runs back. So we could avoid the singularities, and this is something that Karen is going to discuss further, I believe, in particular, by modifying general relativity, modifying the matter sector by sort of dropping one of the energy conditions. So again, the energy conditions were crucial to the focusing aspect, right? For gravity to lead to focusing of geodesics, that was a crucial component of the singularity theorems. You need to have matter satisfying energy conditions. So if you have a violation of actually the average null energy condition, you can avoid the singularity theorems. But then there are two general issues if you do try to do these modifications. One is sometimes you can try to continue through the early singularity into a pre-Big Bang scenario. But a general question is, how do you make sense of continuity and matching conditions in that context? And there's a second question, which I'm just phrasing quite generally, is how much control do we have of the new physics in the sense of understanding the stability properties of this extension and then also understanding how we get classical GR to emerge from whatever the pre-GR description is. So obviously there's been a lot of work on both of those questions, but that's part of what a theory of origins would have to include. And those are being discussed by other talks in this conference. So I'm going for the main part for the rest of this discussion, since I'm focusing on these more philosophical issues. I'm going to be somewhat lazy and say, I'm just going to take the initial state to be something that's specified at like the boundary of applicability of general relativity. Right? So I'm not going to address these further questions that a theory of origins might need to focus on. Now let me come back then to the sort of three general principles that I introduced earlier and see, first of all, how could we formulate them and what is their status in modern cosmology? And I would claim that just as in the 16th and 17th century, when we had the new ideas introduced in how to understand the structure of the solar system, all three of these ideas were pursued by different people. I'd also claim, I'm not going to give the evidence for that here, I claim that it's very clear also that these three different ideas were pursued by cosmologists, especially after the discovery of the cosmic microwave background. And in particular, in 1965, it came as a shock to the cosmology community that the FLRW models worked so damn well. Right? You've got to remember, at 1965, the idea that the FLRW models would work, they probably would have said, they seem to work okay, but maybe 30% accurate, 50%, like they wouldn't have thought that they were extremely accurate, and they especially would not have expected them to apply to the early universe. You observe the CMB and it takes almost 30 years before you discover any isotropy in it other than the dipole isotropy related to our own motion with respect to it. So that's incredible uniformity. And so a lot of cosmologists were inspired to ask, how can we account for this uniformity? And so there are a number of papers in the 60s and 70s that have titles like, Why is the Universe So Isotropic? There's a famous one by Collins and Hawking where they invoke the ensemble idea, and so on. So I'll talk about a few of these, although I'm not going to give the detailed historical evidence. I do want to say something very briefly that there's another historical analog that I think is interesting, which is a place where these kinds of questions came up in a different context, but one that's related, which is that Boltzmann in the 19th century was worried about the source of time asymmetry. And so he had derived the H theorem, which describes how an ideal gas approaches the Maxwell-Boltzmann distribution. And he gave an argument that there's a quantity that will be stationary for that distribution and that you would expect a monotonic increase. Now I forget, the H is opposite of entropy, but anyway, it would monotonically go towards that stationary value. And he was immediately met by colleagues who noted complications because the underlying microscopic dynamics is time reversal invariant. Then you'd also expect a recurrence time, so you can't have a monotonic change in H if it will also eventually have a periodic return to its initial value. So these led him to actually indulge in some cosmological speculations. Again, this is going way back before 1965, but Boltzmann proposed in response to these criticisms of the H theorem two speculative hypotheses that he thought you could help, that you could use cosmological proposals to help understand the nature of time asymmetry. And so one is a version of what I called earlier selection, namely that the entire universe finds itself at present in a very improbable state. And in particular, he thought that the universe began in a low entropy state, and entropy has increased, but is still very low compared to its maximum value. And he also proposed, I mean, this is kind of covering all your bases, I guess, as an approach, proposed another speculative idea, which is the possibility that the universe overall is in a global state of equilibrium, and then there are fluctuations away from that equilibrium, and those local fluctuations can then account for our experience, that we're embedded in one of these local fluctuations away from a global state of equilibrium. And so as he says, the universe is in thermal equilibrium as a whole, and therefore dead, but for relatively small regions of the size of our galaxy, which we call worlds, which during the relatively short time of eons deviate significantly from thermal equilibrium. So I think we can actually see that these two ideas also get instantiated in recent work in cosmology. So now I'm going to shift to looking at some of the modern versions of selection, the idea of an ensemble. I'll say something very brief about these two, and I'll have a little bit more to say about the idea of indifference, which I think has been more influential in cosmology. So again, what's the idea of selection? It's the idea that there's something that selects a particular initial state. So I've listed here a few proposals about how you might select an initial state. And I should say one qualifier. These sort of general methodological orientations don't map cleanly onto research programs in cosmology. So for example, I could put Starobinsky's initial proposal for an inflation-like model on this list because he initially formulated it just as a claim that the universe started in a de Sitter state and then decayed from that. Right? So his initial proposal, although I think inflation, the way it's been practiced since, is more associated with the idea that we should wash away dependence on initial conditions. In at least one version of inflation really takes this kind of approach, that you postulate an initial state and then look for its consequences. Now obviously this would be an appealing position if you had a unique initial state or a small class of initial states that you could select by some basic physical principles, and then the consequences of that selection were compatible with observations. That would be a very appealing position for cosmologists. And so there's been a few proposals. The Weyl curvature hypothesis is maybe most closely related to the Boltzmannian themes I was just discussing, where Penrose basically recognizes that the Weyl curvature in the FLRW models is zero, so there's no gravitational waves, no gravitational degrees of freedom, and then takes that as characterizing a low entropy initial state. These other proposals are also proposals for how to characterize the ground state of the universe. And the CPT universe, that's just a recent proposal that claims that there should be a symmetry that will dictate what the initial state should be. So you can see that there are different types of motivations for a particular constraint on the initial state. I'm just going to say very generally, I think there are two challenges that these kinds of proposals face. One is just, do they actually follow from other fundamental physical principles, or are they consistent with other aspects of physics? And so, for example, Penrose is very clear that he hopes the Weyl curvature hypothesis will be a consequence of some theory of quantum gravity, but it's not been shown to be that. And secondly, and this is really quite above my pay grade, there's a lot of discussions of whether these different proposals have been given a mathematically consistent formulation. So there's recently been a lot of discussion about the no boundary proposal in particular. Feldbrugge and co-authors have suggested that there's a different way of evaluating path integrals in a Lorentzian setting that gives different answers than the traditional way of doing Euclidean path integrals. And so there's been an active debate about what is actually the content of the no boundary proposal as a result. Again, that's above my pay grade, but at this point I think it's unsettled exactly what the content of that proposal would be and what its further implications are for cosmology. And ensemble is also a very popular view. I mentioned that Collins and Hawking had a paper soon after the CMB. This was, and the title is Why is the Universe Isotropic? And the answer was, in effect, if we had an ensemble of universes and we selected ones that are compatible with what we see, that would explain the isotropy. So it's an early version of a kind of anthropic argument. And there have been multiverses of many kinds proposed since then. And some of them are more closely like Boltzmann's initial idea that you imagine somehow characterizing a global equilibrium state and then have fluctuations away from that. But here, again, I'll be fairly brief. I think there's some basic questions about any of these proposals that I think of at least as quite challenging questions for them to address. So one is just first, what actually generates the ensemble and the expected variation among the elements of that ensemble. So why is it that you would expect different regions to have, say, different values of the fundamental constants? And do you have any control over how that is generated? What's the understanding of the physics that's used to generate this ensemble? Furthermore, in this literature, there are often probabilistic claims about how probable is the value of a particular value of the cosmological constant if you accept the idea that there's an ensemble, and then you select the places in that ensemble that are compatible with our existence. It's usually some proxy, such as the existence of large gravitationally bound systems like galaxies. I think it's really hard to justify those sorts of probability assignments, that there just isn't sufficient structure to have unique probabilistic arguments there. Again, this is my own position, but it's not an unusual one. I think there's a lot of people who are worried about the status of these kinds of arguments. And then there's also a kind of argument which I've called anthropic preemption, which is that if you imagine saying, again, if you think of one of these situations as more like a Boltzmann style scenario, if you ask what's the entropy cost associated with a small fluctuation away from equilibrium that's compatible with the evidence we have versus a large fluctuation that would include the entire Hubble volume, then obviously the small fluctuation, this is usually called the Boltzmann brain, if you have a small fluctuation that's somehow compatible with our evidence, that will be vastly higher in terms of probability, at least as these arguments usually go, than the full fluctuation for our entire Hubble volume. And so why is it that you'd expect to see the entire Hubble volume as it is, as opposed to just small fluctuations away that are sort of minimally compatible with our evidence? And I think that's actually, if you try to use, so if you try to use the ensemble point of view and follow it through, I think it's really hard to counter that kind of argument from within the ensemble view. My own position is I'm not, I sort of get off the train a bit earlier, so it's not something that I think is a general problem for cosmology, but I think it's if you accept all of the other elements of the ensemble view, then I think it's a severe challenge. But I want to focus more attention on what I think of as the more prominent methodological view that's been important in cosmology. I want to go back not just to show you a nice 1950s ad for a kitchen implement. This is an early version of an idea that probably you haven't encountered before. This is Misner, again writing soon after the discovery of the cosmic microwave background, introduced what he ended up calling the Mixmaster universe, inspired by the Sunbeam Mixmaster in his kitchen. He was very clear in the 60s in saying that he wanted to think of cosmology as giving predictions of the properties of the universe. Right? So he articulated this program that cosmologists should aim to show what properties the universe has to have independent of initial conditions. Now, it was in pursuing this idea, and he thought that neutrino viscosity, for example, could smooth out initial perturbations to help enhance isotropy. It's in the context of this work that he discovered the horizon problem. And then he proposed that actually, and this is related to the BKL idea that Marie mentioned, that you could actually have, as you approach a singularity, a series of oscillations in different directions. Those are the Mixmaster oscillations. So he proposed that as a way of solving the horizon problem. But again, the hope was that through this series of oscillations and the physical mechanism of neutrino viscosity, you could take a very highly anisotropic model and make it isotropic by virtue of this early phase of dynamics. Now, it turned out that that program didn't work, but I think it illustrates the kind of approach which I'm calling indifference. So the appeal is that you could have a dynamical phase of evolution at a particular stage that washes away the dependence on an initial state. So that you start with an arbitrary or almost arbitrary initial state, and then at some state you have, as a result of the dynamics, that the universe has some set of properties. And this either renders the properties more probable or even probability 1, by contrast with just assuming that they were features of the initial state. Right? So that the argument for the dynamics is supposed to be based on its ability to solve these sorts of fine-tuning problems. Now, I think that that kind of view, although it's quite prevalent, I think it reflects a mistake about how to think about probabilities and inferences in cosmology. And so in particular, if you think about just the standard way that statistical mechanics is applied in cosmology, we have a variety of phases of the universe that we describe using irreversible dynamical equations. So we have freeze out of particle species and decoupling, structure formation by gravitational clumping, and so on. And so the transport equations and other equations we use to describe these features are actually irreversible equations, even though the underlying microscopic physics is reversible. And so I think in this context, we have to think about historical inferences and how to assign probabilities in a different way. And so here's an example that gives the contrast. There are some cases where we can make retrodictions where we just can evolve things deterministically backwards. So to first order at least, when we think about the CMB photons propagating from the surface of last scattering to our telescopes, we can treat those as evolving adiabatically. And so in this case, we can take the present state and evolve those backwards and get a deterministic evolution to the earlier state, back to the surface of last scattering. But this is really the counterexample. In most other cases, if you try to take the present state and evolve backwards, you get kind of ridiculous results. And that's because in the expanding universe, again, this is just sort of a quick review of things that you've seen before in cosmology probably. The universe expands too fast for local interactions to maintain equilibrium. And so we have a series of phases in the universe's history where we have particles freeze out of equilibrium as their interaction rate changes in relation to the local, to the expansion rate. And so, so in describing these processes, you start off with like particle species that can maintain local equilibrium, but then they freeze out. And the way you describe this is using a Boltzmann equation or a coupled set of equations, and those themselves are irreversible equations. And so take, for example, Big Bang nucleosynthesis. So we have neutrons, protons, other particles that start in a local equilibrium, so they're relatively insensitive to the earlier states prior to that. But then we have irreversible dynamics that leads to mass fractions for the light elements. I mean, obviously a very complicated set of equations, but the most important thing is that they're these sort of macroscopic irreversible equations. And so the problem I have with the reasoning behind the indifference idea is that it seems to think about probabilities in this context in the wrong way. So imagine we ask the question in the following way: how probable is Big Bang nucleosynthesis? So imagine we try to count trajectories and we consider the final macro state of the system of some part of the universe after Big Bang nucleosynthesis has taken place. And we say, well, look, the underlying microscopic physics, the nuclear physics that's involved in those interactions, is time reversal invariant. And so we can say, if we try to use a trajectory counting argument that reflects that time reversal invariance, and this is just the standard reversibility problem that Boltzmann already saw, we would say that if you take that macroscopic state, the final state, the vast majority of the trajectories through that did not actually pass through a lower entropy state pre-Big Bang nucleosynthesis. This is just the idea that take the state at any time and the entropy curve would go up in either direction, right? And so we would think instead, if we use this kind of naive trajectory counting argument, that the final state after Big Bang nucleosynthesis should actually be an entropy minimum for the vast majority of trajectories. But that just reflects a mistake. When we're trying to retrodict about the past in a situation that is described using irreversible dynamics, that's not the proper way to reason about those earlier states. So we could try to fix that up by inserting the past hypothesis, where we just said there was an earlier state that had even lower entropy. But I think the more basic point is that this way of thinking about retrodictions and the probabilities associated with them just doesn't really apply in this kind of case. And here I've been influenced by some work by David and also my colleague Wayne Mervold. I think we should think about this in a different kind of way, which I'll just sketch here, although this is probably worth a lot more discussion. That what's going on is we should think of the Big Bang nucleosynthesis case as an example of a kind of dynamical attractor. And in thinking about this, the important point is that we would have initial distributions that converge towards an equilibrium state. The outcome of the Big Bang nucleosynthesis, the final state, is something that a lot of initial states converge towards. And when we assign probabilities, we need to think of them as applying after some relaxation time. So after the dynamical attractor has had sufficient time, then we can apply probabilities. And the important constraint on initial states isn't that it's a low entropy state, it's that there are states that would have delicate correlations among the particles that would lead to not satisfying the irreversible dynamics. So this is easier to see in the case of Boltzmann's original H theorem. So take, some of you have a cup of coffee, I'm sure, in front of you. Take the molecules in that cup of coffee, take their current state, reverse all of the momenta, and that would be a state that would not evolve towards cooling off in the future, right? Because of the correlations that exist among the particles, it would then rewind its microscopic trajectory, which goes to actually a state of higher temperature. So the constraint on the initial state is that the particles can't have those sorts of correlations that would lead to anti-thermodynamic behavior. And that's a little more, that's not quite just saying that it has a low entropy. And so my claim is that in this context, there's a different way of thinking about historical inferences that we should adopt, which is that we should actually just propose an initial state, evolve forward, and then check the consequences. And we have to then assess whether it's plausible to say that that initial state lacks the kinds of delicate correlations that would mean that it's incompatible with the irreversible dynamics that we're using to describe the macroscopic evolution. So my proposal is that when we think about this kind of question, how probable is Big Bang nucleosynthesis, we should formulate the question in a different way. We should ask, is there a plausible initial state before Big Bang nucleosynthesis that would be compatible with the irreversible dynamics that governs the nuclear reactions through Big Bang nucleosynthesis itself. So, and I think we can make this case that we would think that the earlier evolution of the system prior to Big Bang nucleosynthesis leads to washing out the kind of correlations that would be a problem. So we, I think, can assert that that is a plausible initial state. And then when we accept Big Bang nucleosynthesis, it's not because it solves some fine-tuning problem, that the light element abundances are fine-tuned in the standard Big Bang model. It's that we have a very plausible physics for this scale, like the nuclear physics here is not really in question. And that when we forward evolve using this physics, applying it to the earlier state, we get mass fractions for light elements that are both compatible with what we observe, or more, probably better put, they allow us to constrain other parameters, such as the total baryonic mass, in a way that's compatible with what we observe. Right? So the case for Big Bang nucleosynthesis should be taken in this sense, rather than it solving fine-tuning problems. Now, I don't think this is controversial in saying this about Big Bang nucleosynthesis, but my claim is that this is a better way of thinking about earlier phases of the dynamical evolution of the universe as well, as opposed to thinking that those earlier phases solve fine-tuning problems. Because I think the way of thinking about solving fine-tuning problems involves these misconceptions about probabilities and historical inferences. So then, and this is, I'll wrap up here. So then my claims about this final idea, indifference, is that I think the standard rhetoric about being able to solve fine-tuning problems by washing away dependence on initial states reflects a flawed application of probabilistic ideas and historical inferences in this context. And I think that instead of trying to think that these dynamical phases solve fine-tuning problems, we should ask of any proposed dynamical phase, does it involve a plausible initial state? And if we forward evolve the consequences of that dynamical phase, do we get something that's compatible with observation? Okay, so I'll leave it there and look forward to the discussion. Yeah, go ahead.
So what do you make of the fact that different people put inflation in each of those three different categories?
Yeah, so this is, I'm going to be talking more about inflation in a bit. I think, as I said, I don't think the categories map cleanly onto different proposals. And so, in some sense, there's a worry that the sort of methodological principles might be kind of epiphenomenal. Right? They're sort of a layer above the actual research proposals. I think it's, at one level, it's not surprising that you could end up at a similar physics proposal with different sort of heuristic ideas, right? I think in the case of inflation, I think partly the reason why a lot of people now accept an ensemble point of view is partly because of the sort of specific challenges within the initial way of thinking about inflation. So I think you kind of see a movement to eternal inflation that's driven by problems within inflation. So in that case, I think it's really at least Guth and a lot of the people in America working on inflation, the initial rhetoric was all about indifference and washing away fine-tuning problems. But yeah, so I think there's an overall question which is that might undermine the idea that these principles are really important in assessing the programs themselves, which I'm comfortable with, saying let's separate the actual research proposal from the principle driving it. But the problem is, I think in a lot of cases within physics, these sort of background principles get sort of enmeshed with the evaluation of the physics itself, right? So if you look at the way people make a case for inflation, there's often some kind of background reasoning about indifference that plays a crucial role. And I'm fine saying that might not be, maybe we can separate that off. But I think we should try to do that so that we can say, what is actually the empirical case in favor of inflation, separate from this sort of background set of assumptions about what kind of theory a theory of the early universe should be. Yeah, go ahead.
Yeah, so you don't take as a negative fact that a particular physical theoretical framework can navigate between those three different principles at people's wishes, basically?
Well, I mean, it's negative in one sense that it reveals, so again, it might reveal that you failed in one in one attempt and now you've tried to relocate it in another. So if you're really convinced that the ensemble way was, the appropriate way of thinking about things and you're forced out of it, then that would be a failure. I don't know. Yeah, I guess it depends on how committed someone is to the principle and how much they see that as an essential part of the argument. If they do, then obviously it's quite a problem. My focus is more on trying to disentangle things a bit, because I mean, it should be clear I'm fairly skeptical of these sorts of methodological principles in general, and I also think the way they've been instantiated in these discussions in early universe cosmology involves some confusion. So that's my reasons for trying to separate things out. Again, other people might have some a priori commitments that would lead them to say, oh, this is the right principle, and then if that failed, that would be a much more telling failure. I think she had a finger.
Oh, finger?
Yeah.
So I just wanted to understand why eternal inflation would be a move to an ensemble principle with something like the anthropic principle, because from what I understood of Carroll and Chen's model, or even Smolin's model, there was a law-like selection principle which made sure that among the ensemble, most of the universes were typical, and that our universe was one of them. So I was just wondering, and Smolin, I know, very much contested the anthropic principles. I was just wondering, would you be okay with saying these two can be combined?
I think there's three different ideas that you're discussing. So I wouldn't say that Carroll and Chen or Smolin are anything like the eternal inflation.
Okay.
So I think they're quite distinct. So Smolin is quite critical of the anthropic principle, but he still wants to generate an ensemble. The main claim he wants to make, compared to what he sees as the problems of anthropic arguments, is he always argues that he can make predictions based on this sort of black hole hypothesis. So, I think that's just a kind of, that's a move that he thinks gives him an advantage over So yeah, so there are variations within the ensemble point of view that are important that I sort of glossed over. But the eternal inflation view, I think it really is crucial that they employ anthropic reasoning, because if you ask what are the reasons that inflation occurred in our past, it's partly, in the whole eternal inflation landscape, there will be lots of regions where inflation did not occur, but the argument is that somehow the fact that inflation occurred in our past is essential to the conditions that are necessary for us to be here. And so you then have a sense that what is it that physically selected the properties of the early universe that allowed inflation to occur? That's anthropically selected. So I think eternal inflation is maybe closest to what I was criticizing there, because it doesn't involve a law-like constraint on the initial conditions. Carroll and Chin is also different because they imagine that you have sort of a global equilibrium, and then you have sort of baby universes nucleating out of that. So that's maybe a little bit more like the Boltzmann proposal. But I'd say that that's also a different form of ensemble view as well.
Yeah, I mean, they actually stipulate there's no such thing as equilibrium and entropy can increase.
But they do have the sort of global de Sitter state in the background,
That's
right?
true.
And then they have the fluctuations away from that creating baby universes. And I actually think there's an ambiguity in what they mean by entropy in that context. But that's,
Right.
yeah.
Yeah, sorry, am I correct in thinking that the focusing theorem can be applied in either direction of time?
Yeah, yeah.
So, in that case, where exactly does the asymmetry come from in the derivation of initial singularity and the final singularity?
It's just the geometrical conditions. So you have the surface, the rays are going like this, then you go backwards and they converge.
Yeah.
If you flipped it, they would converge in the future.
Okay, so what is the justification for that choice initial condition? Is it just observational? Or?
That's just, in the Tolman and Moore case, it's just observational. For Penrose, it's going to the future. You see you have a closed trap surface. That would be likely within a black hole. And so then you'd have the collapse in the future.
Right,
Yeah.
okay.
I wanted to ask what are the criteria of plausibility of the initial state?
Oh, plausibility of the initial state. Yeah, so this is, again, I think, and this is, I'm really drawing on David's work here. So if you have an irreversible macroscopic equation like the Boltzmann H theorem, that transport equation, right? And then you have microscopic reversible dynamics. There are going to be some states that are incompatible with the macroscopic evolution that's described by that equation. So again, the simplest case is to take a system, evolve it forward in time, then reverse all the momenta or the velocities. That state, the microscopic evolution would go backwards, right? So you'd have then anti-thermodynamic behavior. So that evolution would be incompatible with the macroscopic transport equation. And so the condition that you have to impose is to rule out states like that. And I put delicate correlations just because what you would have in the case of evolving your coffee cup forward, you'd have all of the collisions between the molecules would have induced correlations among the positions and velocities of all the molecules. And to have it unwind back to the initial state of higher temperature, you're sort of relying on those delicate correlations to lead to this anti-thermodynamic evolution. And so you have to have an assessment that that kind of state won't be a plausible state for earlier in time. And that really goes back to some sort of condition that you don't have sort of coherent influences coming in from outside that would lead to these sorts of correlations. So there's a kind of background assumption that, and it is still, it's an assumption about the initial state. It's just not as strong as the sort of typical, there's a different character than what you often see when you just say it's a low entropy initial state.
David, got a follow-up.
Yeah. I mean, just to add to that, this is a sort of global and cosmological version of the kind of conditions you will actually find in the derivation of specific non-equilibrium dynamic equations. Typically, what you'll find in those frameworks is that you'll derive, without it making any kind of reversible assumptions, you'll derive a dynamics that is a sum of a unitary piece, a dissipative piece, and a third piece. And then the third piece, at least in terms of forward time, would be a process of sort of delicate correlations combining in certain ways. And then in the non-equilibrium state met literature, you'll make an assumption that the initial state is such that the third term vanishes. And it's relatively easy to give sufficient conditions on the initial state such that the third term vanishes. It's also easy to give heuristic plausibility arguments that those sufficient conditions are very short of being necessary conditions, and that actually fairly generic states will cause that third term to vanish.
Thanks.
So, David, you also had your hand up separately.
Oh, right. Is it my turn? Oh, okay. So I was wondering about going back to the inflation conversation. I mean, the way you were cashing this out, which sounds right, is I've got these three methods. I wonder if you can also sometimes see that as there are particular phenomena in physics that at least sub-communities of the overall community think ought to be explained by certain methods rather than others. So I'm thinking particularly of equilibrium. I mean, you have observations by people like Shelley Goldstein that if you're thinking in probability terms, well, of course, I should expect the same temperature on this side of the night sky as on that side of the night sky because it's much, the fraction of phase space is much larger for given energy than the bit where this fits a bit more than this.
Right.
And the sort of sense, I mean, just trying to reverse engineer how people are thinking, the sort of sense in which that doesn't seem okay is equilibrium is supposed to be explained by attractor arguments.
Right.
I'm not defending that claim, just tacitly, it looks as if what's going on in vacuum thoughts, maybe other features of the world have other explanations or structures, but when I have equilibrium, I want to have an attractor argument as to why I've got it. Does that sound about right?
That sounds, I mean, so the first part of your question is like, are there other, so first of all, equilibrium explanations are wonderful, right? So I can see like a general interest in seeking those and that they should be attractor type arguments. In the case of cosmology in particular, I think there's also an element of, at the time when this was arising, people were also worried about fine-tuning and naturalness in other contexts. So if you look at the way Guth is posing it, it's partly, yeah, you have sort of distant parts of the universe that are uniform temperature, and how could you explain that if they're not in causal contact? But there's also the kind of real emphasis on the naturalness question with regard to flatness. So I think it's not just that attractor behavior. The other thing is I think it's actually quite misleading. This is, I think, more idiosyncratic. But I think it's misleading to think of what inflation does is make causal interactions that would lead to equilibrium possible. Instead, it reduces everything to the behavior of the evolution of one field. So it's not as if there are pre-existing, so like, I think the initial thought was you have pre-existing distribution of matter and energy, you change the causal structure so that matter and energy now has time to equilibrate. And what in fact inflation does is dilute everything else away to insignificance. And if you ask why is really the temperature the same in two different parts of the sky, it's because the inflaton field decayed in the same way in those two different regions. It all goes back to the behavior of the inflaton.
Sure. No, but I mean, point taken. But I guess the point is that what was unsatisfactory in a non-inflation theory, in that different bits of the night sky being at the same temperature when they hadn't been in causal contact, was that explanations of things being at the same temperature should be kind of attractor equilibration. So, yes, so sure, inflation says, oh, one of those patches is going to be kicked out past the
Right. No, and I agree with the intuition, and I think it is. So I don't want to deny that those things are puzzles in the early universe. I just think that some of the ways that they're described seem to involve a sort of a set of assumptions about probabilistic arguments that just don't work in this context. So I would be happy to say, yeah, you want attractor dynamics, but the sort of washing away initial state, that is a bit stronger, and I think also involves a lot of probabilistic assertions that are more problematic.
Sure.
Yes.
I suppose my thought was that, and this is coming back to Goldstein's observation, that if you were happy with probabilistic arguments from the get-go, you shouldn't be particularly bothered about different bits of the night sky being at the same temperature, because there's a relatively robust-looking probability argument that says they should be, because much more of phase space as this was at the same temperature at different temperatures. And that somehow, I mean, when I first heard that argument, I sort of felt something feels unsatisfactory about that. I'm trying to sort of analyse why. I think somewhere in there is the intuition that
Mhm.
mere probability is not the right explanation to why systems are in equilibrium with one another.
Right.
It has to be adapted to that.
I'll have to think more about the Goldstein case. I hadn't actually heard that example put that way. Yeah.
Can I comment on this? So, I guess it really depends, right? Because on one hand, I agree with you that from the phase-based point of view, it seems that there's much more likely that you have the same temperature across the sky. That's because we're ignoring gravity. Like when you put gravity in the system, that becomes a low entropic state, right? So the CMB is not a high entropic state if you also have gravity together. It's actually a low entropic state. So probabilistically speaking, I would say that the CMB state is actually unlikely to happen.
I think I take the point, having said which, I mean, look, so there's given gravitational entropy explanations, there's a legitimate view to say, okay, how weird it is that we live in a largely homogeneous universe with largely homogeneous thermal matter. But even granted the weirdness that we live in a largely homogeneous universe with largely homogeneous thermal matter, once you've established that, then it starts seeming strange that different bits of that thermal matter are
Yeah, I think there's a question back here as well.
Did I understand you correctly that you are skeptical of all of these principles?
Mm-hmm.
So then I just wanted to ask you, because I feel like you're backed into a corner. Either you keep trying to find these prehistoric dynamics, and that goes on eternally, or you come to some sort of initial conditioning. So I was just then wondering how you get around applying some sort of methodological principle to explain whether it's truly, an origin or some sort of self-locating boundary condition.
Yeah, I think the answer is ultimately you just keep doing physics in the sense of seeking empirical guidance and solving foundational problems in conjunction. And I don't think the methodological principles are, the example of Newton was meant to illustrate, look, sometimes they can guide you in the wrong direction, where what you actually needed was just a better understanding of the relevant physics. And ultimately the physics that was relevant was mainly gravitational physics that Newton had available, although obviously it took a long time before the nebular hypothesis was formulated. And so it's partly that I'm skeptical of taking these principles to force physics into a kind of constrained search of the possibility states, right? I think you can still have a search of the different physical possibilities for different early universe scenarios, but I don't think you should say, I don't think these methodological principles are either clear enough in content or have any evidence that they are more likely to yield true theories that says we should only look in the places they indicate. We should instead say, well, we've got foundational problems with the physics we have. There are still empirical anomalies. We should just seek to resolve those. So it's partly that I think if you accept all these methodological principles, you'll have a constraint on what you're doing that I think is actually not justified.
Can I push a bit on this actually?
Yeah.
Because I have a sort of similar concern. I mean, here's the way. Pretend the universe is classical. And pretend we've actually got the fundamental laws. I mean, that, intuitively that leaves lots and lots of interesting puzzles and thoughts to explain. But there's a sort of thought that somebody might say, okay, my laws are deterministic and I know what they are. So what's the explanation of everything in the world? Well, there's a unique initial state such that it's the past time evolution back to the Big Bang at the present state. The initial hypothesis, the initial state was that state. I'm done with physics now. That presumably feels wrong. There's some sense in which we're able to do substantive explanatory work, of which maybe the fact that systems equilibrate given very weak but not vacuous conditions on them is a paramount example. I mean, I share a nervousness about how you can get a conditions of this kind. It does sort of seem that if we don't have something of that kind of play, it's not obvious why we can't just say, well, the initial state is what it was called today.
Yeah, no, I don't mean to be advocating that we can just say the initial state is a group contingent fact and that's the end of the story, because I think the kind of modal arguments that you're alluding to are essential in physics. So what I think so when I said, we should use empirical anomalies and foundational problems in physics to guide our research, I still think we'd be discovering laws or perhaps dynamics that's relevant to the early phases of the evolution of the universe. I do think, though, that there is a role for explanations that invoke contingent facts beyond the dynamics that we should allow. Like, it's not the case that we should, so I think there's a rationalist impulse to say we're going to explain everything through dynamics. And it's striking, looking at cosmology versus other historical sciences, that people just don't have that same impulse. And I think in some cases in cosmology, you might end up at the position where you can try to explain it with the law, or you can explain it as a brute contingent fact, and there's actually no difference for anything else, right? I mean, that's the worry. And in that case, I don't think you gain a lot by saying it's got to be the law versus the contingent fact. And that's, I think, when you get to early universe cosmology, that's problematic, because even if you say there's an inflaton field, the likelihood of creating an inflaton field anywhere else in a particle accelerator is so small that, you know, like, even you would be committed to all kinds of modal claims by accepting inflation rather than sort of a brute contingent fact, but those modal claims don't have implications that you can test. They don't actually guide action. So I think that that's the conflict, but I do think that the explanations we provide ought to allow that there can be some aspects of explanation that involve what appear to be contingent facts. And this is where a lot of physicists are much more likely to complain about the number of constants that appear in the standard model. And I think, well, this might be something we've discovered about the way physics explains the universe, that there is some empirical information that we need, such as the values of the constants, that are important in characterizing the structure of our universe, that feature in the laws but don't have the same status as the laws. And so I'd want to leave that as an open possibility.
I wonder if there's some kind of simplicity constraint that's salient here. So it's something like maybe there's no very interesting distinction between explaining some kind of thing by virtue of the law versus explaining by virtue of some relatively simple, cleanly stated fact, early universe fact. But there is something concerning about the idea that the way we explain some robust regularity in the present day is to posit some horrendously complicated
Right.
Maybe we can only explain by saying it's the past even
Right. Yeah, no, certainly if we were left in that situation, it would not be a particularly appealing explanation by appeal to contingent facts, right? So the appeals to contingent facts that I have in mind are more like, yeah, the value of the constants seems like something that we could say, we can state it simply, we can explain things based on the values of the constants, and that doesn't seem like the horrible mess that, you just get by evolving the current state backwards.
So I'll ask
Yeah.
a question.
Victoria has a question as well.
I was discovering how cyclic models of cosmology is like another grounds. Can you still make similar arguments from a timeless perspective?
Yeah, I haven't thought quite as much about cyclic models. I think some of the main questions about cyclic models are, how do you think about the continuity through what would have been an initial singularity? How do you sort of match them? And then usually there's a big explanatory burden. So a lot of the models, basically, one of the standard requirements for causal structure, a way of accounting for the density perturbations in the CMB causally, is that you have to have a phase where there was dynamical evolution that's sub-Hubble radius that somehow creates those. And so a lot of the cyclic models sort of rely on the fact that there was an earlier phase before the bounce where you could have structure formation that satisfies that sort of causal restriction, and then it sort of continues through the bounce. And so, again, for that to work, you have to have a very specific way of handling the continuity through the bounce. Whether it's an ensemble type view where you're now sampling from a temporally spread out ensemble, yeah, I just really don't know. I haven't thought about that enough. But again, most of the ones I've looked at recently, they really just focus on, we have a late phase of evolution that accounts for structure formation if it's allowed to continue through. And so they give a very different picture of how to think about what is, what is the structure at the singularity, so to speak, and how that evolves forward. And so I don't know that the general worries I had about like the ensemble position would apply to that kind of argument. It's more about the details of the dynamics and whether you have a sufficient understanding of how you evolve through that phase.
Is there also a hand somewhere in the...
Yeah. Okay. Many thanks for the lecture. It was really great. do you think that there is any substantial difference between the different kind of arc of time that we can obtain from these approaches? It seems to be that, I mean, in all of them you have an explanation from the arc of time, but in some of them it depends on initial conditions, or some contingent situation that we can obtain in the universe, but on the other approaches you can have something stronger, like an arc of time built in the irreversible dynamics or something like that. Do you think that that's correct?
So, I don't know that I quite tracked the question. So, I mean, yes, the thermal history in some sense, the way I was describing it, the arrow of time all comes down to the scale factor. And the fact that the scale factor is evolving in a certain way that leads to this, everything else falling out of equilibrium, right? So in that case, in the thermal history, and this is, I think, just sort of standard textbook lore in cosmology, all of the thermodynamic, the sort of details of the thermal history all traces back to that sort of one factor being out of equilibrium. And so that's really how to think of the arrow of time and the thermal history in cosmology. So I'm not sure if I'm addressing your question though. So you're asking about other accounts of...
At some point you said something like, I think that it was in this indifference methodology, you have something like irreversible dynamics in some sense.
Yeah.
So in that case you have an arrow of time that is more or less built into the irreversible dynamics, right?
Yeah.
But on the other approaches, like the selection approach, okay, that depends on having a very specific initial conditions, so everything is contingent of having these specific conditions. So I just was wondering if you see that there's a difference between the kind of explanation that we can obtain to the arrow, from the arrow of time, depending on which approach we
Yeah, no, and it's this is the kind of thing that in the philosophy literature, some people want to say like constraints on the initial state, like the past hypothesis that Albert describes. There's a question of whether that should just be thought of as a law instead of thinking of it as initial state. And I'm sympathetic with that. I don't know that I buy the Humean account of laws overall, but if you accept that in the sort of best systems analysis, sorry if you haven't all heard of this, but some of you have. In the best systems analysis, I think it's very plausible to say that something like the past hypothesis might be one of the elements of the axiom system. So in that case, I think, you would have a law-like explanation of these things.
Okay.
So, JB.
So, sort of following up from the earlier discussion, I'm wondering about something like fine-tuning of constants. I think of some kind of cosmological constant example. So, so there's a case where it's you could just make it a contingent initial condition, but there's also this widespread methodological position in physics that while it wouldn't necessarily be a problem to say that the cosmological constant is this quite small number plus or minus 1.3, it is a problem to say it's this extremely large number, which, by the way, must be exactly this number to 120,000.
Right.
I mean, where would you fit that kind of framework in your structure, and B, what do you think about those?
Yeah, no, I think that's a different kind of, so I would want to draw a distinction between constants where there's a naturalness problem associated with them, like the Higgs mass or the cosmological constant, and other constants, which I think you could sort of more routinely say, well, it has to have some value. The values we see are not that unusual, so there's no real explanatory problem associated with that. So I want to draw a distinction between, there's some people like Smolin who says the fact that the standard model has 20 constants is itself a problem. We ought to be able to explain all that from first principles. That's a different, so I would reject that as being a kind of overdone rationalist demand. But if you have specific naturalness problems, then I think it's a different kind of question, because you then have a reason for saying, again, I'd want to pursue further how to understand naturalness, but you then have a very specific reason for saying the value of the constant we see is somehow implausible or demands further explanation. I think that's a different kind of question than just a general demand to eliminate all the constants.
I mean, that makes sense, but it's just striking that it's at least quite a lot of your trichotomies seems to fit some of the naturalist discussions. So you have people who want, like a dynamical convergence type argument for the constants, so that actually it turns out it's not unnatural when you think about physics.
Right.
You have ensemblists that tend to say, well, we've got multiverse.
Right.
Because it's life conducive, of course, we're in one of the worlds.
Right.
Constant small, even though that's very unusual. And you have pure contingencies that you want to deny the fact that it's emblematic of the constitution.
Right, right. No, that's right. I mean, I think you could have those different positions even for the natural constants, but I was mainly arguing for you can have contingent facts like the values of the other constants, and that just seems completely unproblematic. In terms of the naturalness problems, I'd have to think a little bit more about whether I want.
I can certainly see how you can have split verdict. I can certainly see how your contingentism looks fine for one.
Yeah, yeah.
So, I'll ask one final question. Sort of a counterfactual or counterphysical history.
Mm-hmm.
If in 65 or 67, whenever Mixmaster had worked, Misner succeeded in showing, at least with homogeneity, you get isotropy and all the rest. And then we got Kobe.
And then we got what?
The Kobe satellite.
Ah, right.
Giving
Okay.
us further structure. I can sort of imagine a scenario going, great, we now just have more fine-grained and we're trying to explain the slight memory of a previous epoch in the Mixmaster, kind of like looking in the pudding and finding the little dots that are still there. Isn't this always going to be the case with arguments like Misner's in even the more early universe? Like whenever we get an attempt to explain via this way, there's still going to be a promissory hope that, yeah, but then when we see further fine-grained detail, we'll just relativize with respect to the ignorance, but we're now trying to do that addition. So that, so far, all sounds like...
So I think if you had a viable explanation of the isotropy and then you discovered the anisotropies, the most natural thing to do would be to say, can I tweak it a little bit to also explain the slight anisotropies? I think that's exactly right.
So it starts to seem then that at least one of these trichotomies is slightly of a different kind. It's more of a preliminary or for now type argument, whereas the others, it's not a finality in the sort of like final theorizing about physics, but it's more final as we're getting definite purchase on the particular phenomena at hand.
So you think that like either the ensemble view or the selection view is more, we're going to specify the ground state or leave everything up to selection in an ensemble, and that sort of halts research? Is that the thought? Whereas
or rather, the next question in research will be a furthering sort of beyond that. So either you're pushing further back in time into previous epochs, or you're pushing further in a different direction, whereas the ignorance one leaves open that you can revisit the same suite of questions.
Yeah, I think that's right in some sense. I mean, I think I don't know that it's, so I think with any of them, so again, the sort of principles don't map cleanly onto research programs either. So you could think of Starobinsky as proposing a model for inflation that was really a selection of the initial state of the universe is de Sitter, and then how does that evolve into something like an FLRW model? And if that was your approach, you could imagine just sort of saying, okay, well, let's think about further consequences of what this de Sitter state would look like. And you could imagine developing it in a similar way. And I'd imagine, again, if you were working within the context of a no boundary proposal, you could similarly have an evolution of ideas within that program. So I don't know that any of them are close. I mean, the selection and ensemble, I think, does feel a little bit like throwing up your hands in some ways, right? So it's a little bit less clear how you could have the development of the views within that, because it's you're sort of always able to just say, well, that's just because of the necessary conditions for our existence that we see all these features. And so it seems like the explanatory resources are a bit too rich in some sense. But I think in either of the others, you could imagine a sort of research program developing.
All right, let's thank Chris.